For the project was to create an autonomous rover that could navigate a course. The track of a course would be 6 to 10 inches wider than the rover's width, and walls would serve as the boundaries of the course. Teams could determine the starting and stopping conditions for the rover. The course could be of any configuration. It can be a figure eight, straight, or circular. As examples, any sensors on the rover and its motors would be controlled by PIC microcontrollers. If there were multiple PIC microcontrollers on the rover, then they would communicate over I2C. An ARM board would host a web server and all of our intense processing algorithms. For example, our navigation algorithm was hosted on the ARM board. The PIC microcontrollers and ARM board were required to communicate wirelessly using XBee receiver transmitter pairs.
My name is Miko Boris, and I worked on the message protocol between the ARM and the PIC, most of the ARM code base, and it also included the routing algorithms. In order to test the routing algorithm, we created a dashboard with a fully featured simulator. The simulator, which runs on the ARM, receives delegate messages that would otherwise be sent out via UART to the PIC master. Simulator mode is enabled via preprocessor directive in the Raji rover config, and when the simulator mode is enabled, UART is automatically disabled. Simulation courses can be built easily. They're just PNG files, and they can be added to the simulation course library just by running a script. The Python script converts the PNGs, which have a special color index, into map files. And the map files are interpreted by our map module into a grid system that discerns spaces into walls, finish line area, the rover start, and track space. Although not currently supported, an initial direction could be added as an attribute to the PNG files for an additional simulator option. The simulator turned out to be a great way to debug the routing algorithms and probably a good time saver. We iterated through 3 major routing algorithms, some which only used a subset of the API that we had currently implemented on the physical rover. Here we see the dash, and the green logging messages are coming from client side, and the blue are coming from the ARM board and sent over. So here you can see I've selected a different map, and the proximity values adjust accordingly. So right now the rover is initialized to the start position, as you can see in the log, and as I change maps, the proximity values change because the walls are at different locations on these maps, at least for the rover starting position. Next, we can see a shortcoming of a routing algorithm. Now I've reprogrammed the ARM to use a different iteration of the routing algorithm just by changing a preprocessor directive. And now watch as the simulator behaves differently on the same map we saw before. So it'll get stuck in this spin state here because this iteration of the routing algorithm had too far of a threshold looking forward, and it would spin if it didn't see anything under that threshold.
My name is Tony Angel, and I will go over our rover implementation, including PIC microcontroller setup, motor controller setup, power distribution, and communication between the PICs. Our group decided to use the PIC 2860. We used two of these version 5 boards that go with the PIC 2860. The version 5 board was developed here at Virginia Tech. One major advantage of the version 5 board is that it has several interrupt pins available, which are not available on the V4. We further decided to use the PIC 2860 because by using the same one twice, we were able to know the configuration settings very well, rather than having to change configuration settings for each PIC. This is a slightly disassembled version of our rover. This is the top of our rover, and you can see that we have two PICs. We have one breadboard with an XB wireless on it. The power and ground lines are on this breadboard, and our sensors are located around the rover. On the inside of the rover, we have a 12-volt battery connected to a saber-tooth motor controller. The saber-tooth motor controller regulates the voltage to 5 volts. On our breadboard, we have ground and power. This is 5 volts that's coming from the saber-tooth motor controller. Both of the PICs and the IR sensors, the infrared rangefinder sensors, are connected to that. The XP is also connected to that. So all of our devices are connected to the saber-tooth. Everything has a common ground and is powered from the same place. On our breadboard, we have several capacitors. Each of these capacitors serves a purpose. The 4 smallest capacitors are 10 microfarads, and they're used for when the IR sensors collect data. Anthony will talk about this more later. The larger capacitors are for when the PIC needs, these are decoupling capacitors, and they are for when there are different types of power surges on the board in order to avoid any problems. To demonstrate other aspects of our design, I will remove all of these wires from our breadboard. We had one master PIC and one slave PIC, which communicated over an I2C bus. It's slightly different in our case because this bus is actually what we call the train bus and allows for communication over longer distances. However, the basic idea is still the same. There's one clock line and one data line, and this controls how the devices communicate. It essentially decides if it needs to write to the slave PIC or read from the slave PIC. In our implementation, the master PIC was in charge of communication with the ARM board and communication with the slave PIC. The slave PIC was in charge of issuing motor commands and collecting sensor data. For the motor controller aspect of our project, what we used was UART communication. UART is normally a 2-wire interface. One wire is for receiving information, one wire is for transferring information. In our case, we only needed to transfer information, so there was only one wire connected to the saber-tooth motor controller. We used a simplified protocol where one byte contained all the information we needed to control both motors on the rover. One motor was for the left wheels and one motor was for the right wheels. 1 through 127 had all the meaning that it needed to go: full forward, full reverse, and stop. 1 was full reverse, 63 was full stop, 127 was full forward. Anything between 64 and 127 was some degree of speed forward, and anything between 1 and 162 was some degree of speed backwards. It was analogous in the motors for the right, where anything above 128 had the same mapping of meaning. This simple protocol allowed us to issue 2 bytes, which would control both motors in the case of movement. This allowed us to perform movements such as spinning in place and making different degree turns. In terms of design decisions, we initially wanted to use 3 PICs with the same I2C setup, where one PIC would be master and we would have 2 slave PICs. One slave PIC would be in charge of motor commands, and one slave PIC would be in charge of sensor data. We decided to use 2 PICs in order to reduce power consumption. This also allowed us a simpler version of I2C usage over the bus. It allowed simpler I2C communication because we did not have to worry about needing to issue a motor command while we were collecting data. This way we were able to do whatever we needed to with the slave pick and know exactly what was happening with the slave pick at the time.
Robustness is absolutely something we designed for, and you can see it in both our hardware and our software. If we lose a sensor, the routing algorithm will see the sentinel value we've defined, indicating that the sensor has gone down and will do its best to continue operating. Hardware-wise, we have good power connections and plenty of decoupling capacitors to ensure smooth power distribution to all of the components. If we lose a radio connection, the debug LEDs will clearly indicate that messages aren't properly flowing between the picks and the arm. Conditions don't drastically affect our rover, as the values from the sensors that are reported back to the arm are considered relative to each other. For the most part, however, lighting conditions were constant across our different setups. We either tested in a dorm room or the cell, and both locations are lit by similar fluorescent lights, so infrared sensors aren't affected too much. Furthermore, whenever possible, we use cardboard boxes to construct the courses as much as possible for additional consistency. Provided adequate power, the system should run indefinitely, provided it can return to the start of a course and then it's not blocked in by walls. The system does have some bugs, however, and can occasionally slam into a wall. In this case, a manual driving mode with some commands we've defined can be sent and operated via XCTU or the web interface to get the rover back into a position that it can work from, provided the operator has line of sight. The bulk of my visible work was the mounting and data acquisition of the infrared sensors. We chose infrared because we knew we weren't operating in wide open spaces where sonar would be king. Originally, we planned to mount the sensors in the center of the rover facing outward. By doing this, we would mitigate the minimum rated distance of each sensor. This ended up not being feasible, however, because the bricks used to construct the course were too low, which meant that we had to mount the sensors on the outside of the rover. For the safety of the sensors, we chose to use a two-part Velcro mounting system so that the bracket and sensor could detach from the rover and each other if a collision occurred. This is in contrast to a pretty common L-bracket approach where everything was screwed into the rover and sensors could break if a collision was forceful enough. As you can see from the pictures, our rover utilizes 5 IR sensors facing different locations: left, front, front right, and right. In our testing and design process, this is all we thought we would need and was all we ended up needing. Rear-facing sensors, as some teams used, weren't necessary because the course would not change behind us and we didn't have to worry about other things navigating the course at the same time. In a sort of inductive methodology, we trusted that our past assertions and decisions were correct, and therefore we wouldn't have to backtrack with any added precision or distance values from sensors. If the requirements changed somehow and the course was mutable while we were navigating, our design would certainly have to change. By using the same IR sensor model, our software was remarkably simplified, and any work to enhance the sampling benefited our sensing in every direction. This philosophy really shined toward the end of the course when we focused on getting a good function to map the IR readings to distance values. Any work we did to enhance the front readings affected all of the other sensors in a positive way as well.